Okay, so in the schedule it said HOL, and actually there are a couple of holes, and if I would hear HOL, I would think of HOL 4, the other one. So this is a brief history of the system. So Mike Gordon implemented the first HOL in 1988, at least it's called HOL 88, and that's written in standard ML currently. Poly is standard ML. And that system is very active and is used for computer science mostly. And the system I'm talking about today is HOLite, which is a reimplementation by John Harrison, the other guy over there. It's written in OCaml, like Kok and yeah. So they had a paper around this time called HOL Done Right, which I think John now considers a bit pedantic, but it's a very lightweight re-implementation of the same system. So when there's HOL on the schedule, you should specify it more and say, okay, I'll be talking about HOLites today. Okay. So to put it a bit in context, like Yannick, I want to give a bit of context. So we're here for doing formalization of mathematics. So what are the interesting systems here? So I've been maintaining this list with 100 theorems where I track which theorem has been formalized in which system. And this is the current state. So we have 99 out of 100 done. The one that hasn't been done yet is the Fermat's last theorem, which I'm sure Kevin is putting a lot of energy into right now, so at some point we will get to 100. And this is the current state. So when I was preparing this thing, who is interested in HOLite, just use lean if you want to do mathematics. I mean, all the mathematicians are there. There are lots of people. There's a big zulip with lots of things in it, and Floris and Mario will talk about it later. So why HOLite? But actually HOLite is in this list as well. And Isabel is even higher, and Isabel HOL and HOLite are very similar systems. So somehow it's an interesting system in its own right. So worth looking at. I put little flags to give some. And so does this mean that Isabel HOL is a better system than lean? No, it isn't. Because this list, it's like if there's someone who thinks, oh, this is a nice game formalizing theorems from this list, then this gets the system higher in this list, and if no one turns up like that, then so I looked to formalize more than 20 theorems here, and those 5 people. And as you can see, HOLite is John Harrison's system. He liked the game of getting high in his list, and he formalized for a long time. He was at the top. And MetaMath, as you can see, Mario is here, liked this game. So I think you should take this list with a grain of salt. But for now, I'm going to assume these are the 8 interesting systems. Sorry, PBS, there you didn't have an enthusiastic user like that, so you didn't get high in my list. So let me compare HOLite to the other systems. That's not about HOLite, but still. So this is a bit of a historical diagram. The 4 systems from the 70s, so it was mentioned that the thing started in 69, but the first Automat system was called Automat 68, so I would like to say that's 68. Are those 4 systems, Automat, Nizar, LCF, and the Boy-Moore prover, and they all brought 4 different things into the game. Automat brought proof terms, which is a big thing if you're a Coq-Lean user. Nizar brought declarative proof, so the proof script, you can actually read it as mathematical text instead of just looking at a bunch of tactics. And that didn't really take on so well. Isabel is the main system with the Isar language that has that currently. And to my surprise, Lean didn't copy that. Maybe it will at some point, who knows. Tactics are a big thing. That started with the LCF system, which is the predecessor of the whole system. And the Boyer-Moore prover is like, why do we need to do all this work? We just want to say grind, and then the thing goes away, or we want to say slash hammer and the thing goes away. That's really an NQM thing. Whether these errors are all exactly correct, I don't know. There are 4 more systems here. Automat is the system from my own country that started the whole thing. And LCF and HOL 88 are actually, those three systems, LCF, HOL 88 and HOL Light, are very, very similar. The difference between LCF and HOL 88 is basically logic, not the architecture of the system. And like I said, HOL Light is just a nicer implementation of the whole system. And I put an arrow from LCF to MetaMask, that's probably sillier. I mean, MetaMask had tactics, that's what I want to do. I don't think there's a direct influence there. Okay, so I made a nice table to offend people, because I put minuses if you could have a discussion about this. So let's see. Proof terms I talked about already, and when I say proof terms, I mean in the type-theoretic sense. So the Curry-Howard isomorphism says that the structure of a proof corresponds to the structure of a lambda term, and Kok and Lean have that kind of thing in their logic and their system. The others really don't. So in HOL Light, if you're a fan of Curry-Howard isomorphism, then HOL Light won't give you. Then there's dependent types, whether they're useful. If you talk to Kevin Buzzard, he will tell you it's important. If you look at my list, maybe it's not so important. And then you can say, but this list is about basic mathematics. For real mathematics, we need it. But then in Isabel Hall, they formalized this textbook about modular forms. That's not so basic mathematics, I think. So it's something you can have a discussion on. Then tactics, I used to be a Mizar user, I'm not so much into tactics, but that's one more thing. We have the declarative proof style, and I put MetaMask pluses for both, because you develop a proof using tactics, but then the proof at the end is a declarative text. And then strong proof of automation, why does Kok not have, or Lean not have strong proof of automation? Well, this grind thing, I have something, I don't want to look at it, go away. They're working on it, so it might be, it should be plus minus, but I said, okay, that's good.
Hammers.
Yeah, the hammers, I don't think the hammers are really used already. I mean, sorry, Joseph, but in Isabel, it's an actual thing. The rest is just more research into hammers, but if people are using it, maybe I'm an old guy that is not up to date. I don't know. Anyways. So this is basically the spectrum of systems where I put HOL Light somewhere on the map. Okay, the Brown criterion was mentioned already. It means that you have this. So the Brown actually had a paper that says you should have a rechecker. So your system processes the proof script, builds a proof term or something basic out of it, and then you export that, and then you have a second system, a very small system, probably written in Python or some stupid language, and that rechecks it for you. That's the image of the man. But then, who is going to do this? So a better version of it is that this rechecker is actually the kernel of the system. And there are basically two versions of it. With MetaMath, I'm not totally sure whether it has a kernel like this or not.
It's very, I mean, the whole thing is the kernel.
Okay.
It is a small kernel. That's the entirety of it.
Okay, so maybe I should MetaMath, but it doesn't really fit into the other set. Okay. Anyway, in Kok, what you do is you build the lambda term, that's your proof, and then you give it to the type checker, and the type checks it, and it says it's okay. And in Kok, even the proof terms hang around. In Lean, that's not the case anymore because it's proof relevant. So then you can throw the proof terms away after you have checked them. But that in Isabel, in the LCF derivative systems is different. What you do is you do the proof in tiny little steps, and after every step you say, okay, that's okay, and then you forget what the proof was. And the image that Hausdorff always uses for this is these ephemeral proofs. Someone writes the proof in the sand on the beach, and then simultaneously the sea comes and washes it away. And at the end you know everything was correct because you were there when it happened, but there's nothing left. And it's kind of nice because it makes it very memory efficient. I mean, if you could do a huge Holite proof check, then if you look in the usage of the process, it will be tiny. So the garbage collector will have garbage collected everything away. So this is different from the other two systems, and I wanted to point out this difference. Okay, we already talked about set theory. So if you look at MetaMath and Nizar, so people who are not into set theory always say set theory is nice for theory, but in practice it doesn't work. In practice it perfectly works, it's just a matter of taste. But again, I took those 8 systems and looked at the logical foundations. The whole systems and the dependent type theory systems both use type theory, but in a very different way. So, like PBS HOL is classical. Now what can I say about this slide? Let's move on to this. Okay, this is just to do justice to some other people. There are more HOL systems out there. Like I said, the LCF system is the original system from long ago. HOL was kind of close to this. So it's been around very long. And there are lots of derivatives. So here people have toyed with the logic because the whole logic is kind of weak, so they try to make it more polymorphic. Jacques, who will be later, has a version of it. Mark Adams has a version in which he tries very hard to make sure it's consistent in all kinds of ways. And Kendall I will talk about a bit later. So when you say whole, exactly what system you're talking about is kind of up for grabs. Okay, so self-verification. We talked about small kernels. Yeah, Yannick talked about this. If you look at the Coq kernel, it's not small. There's a complete implementation of OCaml inside in some way. So doing the Metacoq thing, and I understand that in Lean something like this is going on right now. Mario's been working on this. I wish them luck. But those logic are not simple. The whole logic is extremely simple. It has only 10 actually it's 9 inference rules. One of those inference rules is there for efficiency. It's like this, and in a later talk I will give the details of this. The Holite kernel is also very, very small. Not as small as MetaMath, I'm sure, but it's 385 lines, and that's including all the optimizations to make it efficient. It's really, really simple. About bugs in the system, 1 bug a year in Coq, I was kind of surprised by that. That looks like a lot. So I like this a lot. When John was visiting me, I made a t-shirt for him with the source of Holite on it. And at that point, 2 soundness bugs were found. So I said, okay, we should patch the t-shirt and put a little correction on it. I think that those were the last soundness bugs that were found. And that was early 2000s. I mean, this is a very, very solid system. So, John then said, okay, this was embarrassing, let's prove the correctness of my code. And he really proved the correctness of the actual code. So, in Coq and in Lean, trying to formalize the kernel resembles the real system, but it's just a simplified version and it's not a thing you're running every day. In HOL, you really verify the correctness of the kernel, that's the workhorse kernel. And there are various variants, what does it mean to prove this kernel correct? Okay, I should have turned off my, sorry. Okay. So, Gödel says a system cannot prove its own correctness. So you need to fumble a little bit. And there are 2 ways to do this. One is you don't include infinity axiom, so you leave out one of those 3 axioms, and then the system, and of course for the correctness of the code it doesn't make any difference. Or you put a big cardinal assumption that you have for which you can get a model, and then that's a 1 line. And you're talking about proving 385 lines of ML correct, so all the work won't be tainted too much by that. Then there's of course the philosophical problem. Use the system to prove its own correctness. So what if the system is incorrect and accepted for this reason? That's philosophy, I don't think that's interesting. Okay, so after John did this, there were more projects like this. So, yeah, I need to speed up. Okay, thank you.
There are people that they should come back.
Yeah, talk to me all you like. Yeah, I'm fine with this. Okay, so what happened was, what John did, he took the code and just made equivalent HOL definitions which looked very similar. In the KKMO project, they have a verified version of ML in HOL 4, not in HOL Light. It's very much like Consort, only nicer. For various reasons, if you want to know why I like it better, talk to me. And then they really proved the correctness of the code with that the KKML semantics. And they, Oscar Amundsen did a follow-up thing, so they now really have a clone of HOL Light running in KKML that can basically do all that HOL Light can do. There, I think Metis is not supported, but apart from that, it's mostly the system. And they didn't just prove the kernel correct, they also proved that everything on top of that couldn't prove incorrect things. So, if you want to know more about this, look at it or talk to me. Okay, applications. So, John has been using this in his day-to-day job, first at Intel and then at Amazon. There was the FlySpec project. Tom had his proof of the Kepler conjecture and wanted to verify it, and he was considering Coq, and then he made a mistake to talk to me, and I said, you should look at HOL Light, and then he decided to go to HOL Light. There's one lemma that has been done in Isabel that's a bit of a weaker point of it, but still. And then I was at AITP, which is Jozef's and Cesari's conference on AI for mathematics, and there was these people from Google Research making the LLMs do mathematics, and to my surprise they selected HOL Light. And the reason for that is that HOL Light is very easy and open system, easy to hack. So to my surprise they were using HOL Light for this. Okay, so here are some dimensions. How many minutes do I have? 2? 1? 3. Okay, it's a huge library, lots and lots of mathematics. John is a genius, he formalized all that himself. But it's not trivial mathematics. I mean, it's not on the level of the Tasker-Narcisse theorem or something like this. There are really complicated mathematical theorems there. Automation is strong, like I said, lots of decision procedures. It's not on the level of the hammers, but the system is known for. Extensibility is easy. It's a trivial system. You're really working under inside the engine. So there's no understanding how to extend it. If you would do that in Lean, you need to read the manual and understand lots of stuff. In HOL, it's trivial. It's very flat. There are no modules, no namespaces. It's just a bunch of files that get loaded one by one. It's a trivial thing. I like that a lot. Most computer scientists don't like that at all, but that's their problem. Backward compatibility is high. So in Coq it was said that as backward compatibility is high. I don't believe that because I've been a Coq user for a long time. And especially I have a system that society developed that broke because the feature of Coq use was not maintained. But HOL Light, if you take something from 10 years ago, it will just run. I mean, it's a one-person system who likes what he did, so it's still changing. It's very fast. The whole standards library, if it takes 1 minute to check it. In fact, you need to do that every time you start a system, so it's a good thing it's fast. Like I said, the memory footprint is small because of the ephemeral proofs. There is no syntactic sugar. You have numerals, you have uploaded operators, and that's about it. So there are no coercions, no type classes. It's what you see is what you get in the front line. There's no interface, none whatsoever. You just type OCaml expressions. The help system is nice. There's search. That's all very nice. Okay, if you want to try it, go to one of these web pages, just Google HOL Light and you will find them. There's a new one that Google won't know about that John pointed out to me. If you want to know more about how to use it, there are 2 nice documents that John wrote. And what does it look like? So here is an example. I took a random proof from one of the files. one of the top 100 files. So this is the mathematical thing on the top. In HOLite it looks like this. So you have a statement, and this is what HOLite tactics look like. For some reason they like the caps key, I suppose. Okay, that was it. Thank you.